Okay, so my paper is, the paper I'm presenting today is called CS2, a controllable and simultaneous synthesizer of images and annotations with minimal human intervention. So the motivation of this paper is that it's basically saying that creating masks, especially for segmentations, is something that's very time intensive. It leads to errors, but also the problem is because it requires so much time. It's usually done by many people, and when it's done by many people, each person has their own bias. So the masks look different based on who made it, but the main problem being that it takes a lot of time. So the solution, and also we're dealing with CT scan images. Those are long that we're seeing here, and that's what we're trying to annotate. So the solution here is to using real, CT scan images and passing it through a synthesizer, so generative models and stuff like that, to create new images of CT scans with their respective label for segmentation, which is what we're seeing here. We're also seeing two colors. So we're trying to capture, for this data set, we're trying to capture the lung, but also there's this GGO, which is basically caused by disease, cancer, and etc. And so in the image, it creates this white that we're seeing here. And so here it's being segmented as well. This is already something that's possible. So we have with generative models, so there's multiple ways of creating those paired of images and label, so segmentation label. We can pass it, once it's trained, we can pass it a vector, and then a generative model will transform that into a new CT scan image, and then through an algorithm, it will create the segmentation for it. Otherwise, we can just use one mask, and then create the corresponding CT scan, or we can kind of combine and pass in just a random vector, and it will give us, through generative models, it will give us that segmentation. And using another generative model, we can have the CT scan that corresponds to the mask. And so while those methods exist, they're not the best performing. And so we'll come back to that. But here's the approach of this paper. It's a bit more complex. So we have an original, So we have an original CT scan. We're gonna pass it through a mask generation that's unsupervised, so we're not using any labels, and it's gonna give us an HU value map, HU being the density, because here the color will represent density in CT scans. So basically, instead of having maybe hundreds, thousand different colors, different types of things we're seeing in the image, here we're basically clustering, and we're making, we have the lungs, that's one color, so the color is gonna be the mean color that we had over here, so the mean density, and then we're gonna do that for the other parts of the image. So once we have that value map, which is kind of a first mask that we're gonna use, we're gonna combine it with another CT scan, which we'll come back to why we're doing this, but it's to give us more perception on what is a CT scan supposed to be, and it's giving us like two different images, so we can generate a different image. So passing that through the GAN part of the model, we're gonna get a first, so we're gonna get a new created CT scan, and then we're also gonna pass the output to a classifier that's pixel wise, so it will tell if it's either the lung, the GGO part of the lung, or nothing at all. And then we'll have our segmentation image that's made for the CT scan that we created earlier. So I'm gonna go into the unsupervised mask generation, which is a pretty complex part of the model. So it starts with something very simple. So we have the original CT scan that's being passed into a conventional neural network. And as always, we have the feature maps that are being outputted. And then what we're gonna do is for each feature, for each feature map, we're gonna take the, for each pixel on the feature on this, on the dimension. So here it's 24 by 224. We're gonna take which feature map had the highest value. So here, for example, the goal of this is like here, for example, if the lungs is what's really being represented in this feature map, then this, the first one that we're seeing is going to represent the lungs. Then maybe the second one will represent that part, which is the bones, etc., etc. And so that's our first segmentation, but that's nothing near what we want to do. So a second thing we do is we create those super pixels. And here it's simply some sort of clustering that we're applying. And it's basically clustering on color and proximity. So what it's doing here actually is that it's going to put together pixels to create some objects so that, for example, this little thing that we're seeing here, the little circle, we don't want that to be assigned to two different labels because it's close, the pixels are close together and they're in the same density color. So it's basically creating clusters and telling which pixels should stay together in the same label. And so when you combine that to the first segmentation, we get our final segmentation. Whereas where I cited, we do use those colors to say what stays in the same label. And we have a final segmentation. So that's more of what we want to see. And we're going to train this because we're going to loop over and over again. And so the way we're training it is we're going to compute a cross entropy loss between the final segmentation and the feature maps. So of course, there's many feature maps. The way we're doing it is which feature maps represents each cluster, each color. And so we're gonna do one color, we're gonna see which feature map represents its best, and then we're gonna compute the cross entropy loss between each pixel. And then that's how we train the CNN. So once we have that, we don't want to keep those colors. So we assign each category or cluster, each label to its mean HU value, which is the color. So here the mean color for the yellow thing was, very white. So we have that again. And then the lungs being blue here, where this gray. So then we have original image, but it's kind of the first, it's a first segmentation that we're doing. So our first mask. Then how we're going to use this is once we have our value map, we're going to want to pass that into the GAN part of the model. So as mentioned earlier, we do add a non-corresponding CT scan. And the way it's going to work is we're going to pass it through an encoder at first. And then the mask is going to give us a feature maps representing the content. And the non-corresponding CT scan is going to give us feature maps that correspond to the style. So here we have content and style features. So the style features represent the visual characteristic of the organs. And then the content features represent the shape and position of the organs. So here for the lungs, we're going to have the shape of it taken here, and we're going to have the color and the different styles, so little white lines, etc., from that CT scan image. Next up, we're going to use those features into the GAN and the decoders. So oh, my bad, I realized I wasn't pointing. So we pass the style features to actually we pass the at first we pass the content features into the first GAN, which here is at a aim, and we pass it at the beginning of the decoder, where the style features are different because we're passing it to the conventional blocks, but we're basically adding it to each conventional block. And that's where it's really going to help kind of create the mask part, so like the segmentation of the image. So the first thing we get out of this decoder is we get our synthesized CD image, which you can see is different. If you look at the shape here, there's nothing like this one or nothing like this one. So we created a new CD scan image. Then what we're also seeing is that, but actually one question we might have is, how do we train this? How do we say this? How do we know if this image has been well generated? Does it correspond to a CD scan? Are we generating? What if what we're generating is it biomedically correct? So this is where the paper computed 3 losses, and then adds them together to get the final loss, which is going to be put back in both the encoder and the decoder. So the first one is a discriminator loss, which is often used in GANs. It's basically asking the city scan if it's real or not. And so we're going to pass images into that, and it's going to be able to determine whether or not it's real. And we want, of course, this city scan to appear as real. Then we're going to pass a style matching loss. So what we can do here is we pass the city scan back in the encoder. It's going to give us style features, and we compare them to the style features from the reference CD image, because it should have the same style. And lastly, we do the same thing for content. However, the paper doesn't really explain too much on how the content one is being made. The loss overalls are not really well explained, but the idea here is really to see if the content is matching what we gave it, if the style is matching what we gave it, and if this can be believed as a real CT scan image. And next up, we're going to want to generate the CT label, so the mask. So here we have an MLP. So the MLP is trained with 30 synthetic images label. So the way it works is that of those generated images, 30 of those generated images, 30 of them were actually trained. Were actually, sorry for that. So 30 of them were actually given, like a person was able to draw the label we were expecting for that specific image, and that's how we use to train the MLPs. It seems like a very low amount. We'll come back on that, which is, that's kind of the purpose of the paper, is to train it on like a very low amount of images. And then here, when we talk about a sample, is that we want to pass in the same dimension as the actual image. So instead of using, a lot of feature maps, we make it into one big image. So here's the resolution is 324/24. And so we're concatenating and upsampling it so it has the same resolution. So that's it for the model. The next thing we want to know is, how does this perform? So we did talk about using only 30 images. So here we're seeing, we're computing dice, which is a scoring method to compare the segmentation masks. And so here we have the lung, the GGO. So the GGO is the cancer part. And then, so we have the own data set and a public data set. So what the main thing we can see here is that you have to look at the the X scale. So it sees this is the scores we're getting with our algorithm on 5, 10, 20, 25, 30 trained images. What we're seeing here is that with 30 we get maybe 95% accuracy. On a mask to image GAN that we talked about in the past, we get a 0%, and it's always the case. So to get some kind of scores around the 90s, we need a minimum of 100. Minimum of 100 images, and that's where the whole point of this paper goes, is that we're really able to, with a few amount of images, we can actually have some really good results. And so, the results can continue for the same thing. So it never works on 30, but we get really good results right away. So that's the main part. We also, the paper also talked about, visually, is what we're seeing correct or non-correct? So first of all, we're comparing the different methods we talked about in the past. So the first one is vector to image. Here we're seeing no GGO, so the green part. It's basically qualifying this part, which is white, as bones. But this white zone is actually supposed to be the GGO, so it's failing to do so. The vector to mask to image, the problem is the long edges. So if you see like the color, maybe the color, for example, the green, it's like tiny pieces here and there, which isn't really supposed to be that way. And it's categorized and not really well segmented. Then we have the GGO edges, which are said to be incorrect. There's not much to interpret here as non-medical experts. But the point is, with the three different GANs, biomedical experts look at this and say, okay, no, there's something wrong. Like the mass we're generating are not the way we want it. But everything seems right on the CS2. The images, the scans, the mass generated are correct by the people that were able to test the results. So they were happy with that. And that's it for the paper. That's all we have, all the information we have. So I want to talk about the strength and the weaknesses. So in terms of strength, it's something that's very novel. The fact that it's creating both CT scans and its annotations, and the whole method is, there's no really, it comes, compares it to small GANs. It doesn't, it's not like a method that had most of it already. So the unsupervised mass creation and combining, adding the style part to the GANs is something that wasn't really done until this paper. So that's a lot of novelty. This problem that they put, of not having enough mask, it's something that's, especially for segmentation, where it takes a while to create them, it's something that's actually really often encountered. So it solves a real world problem right away. And so, having those 30 masks as the site is something that's not too hard to do. And then being able to create like another 100 is something that's like basically that could be done by a lot of people, and that would help them right away. So that's something very nice in this paper. And then the results are very good with a low amount of training. The scoring methods are correct. Everything seems good, and also the scored on multiple data sets. So that was nice to see. The weaknesses, however, is that especially for I found the unsupervised mass generation, it's only applicable to this one data set. To this one type of data, which is the lungs and the CT scans. So if it was something else, probably it wouldn't work. So I mean that's a normal thing to see, but you know, it has limited application. The validation part could have been more. It could have been more because we have those images, we have those dice scores, but it's not like we had like a lot of biomedical approach to, you know, whether the results were correct. We don't see that much in the paper. And then I would say a lack of details. I found out when analyzing the paper. So between the losses that weren't very clear, a few stuff in the unsupervised match generation, but also in the testing part. I mean the scoring part. The paper could have explained a few things better. So that's my opinion on it. And then the conclusion is that you know, it's useful and effective right away, which is nice. And I think it has a potential to be used right away. But it could be, I feel like it needs more work. It could, you know, for scoring it, for providing more details, maybe trying to apply it to different data. You know, that could lead to a very interesting, more and more interesting papers. So my overall rating is a good 3. And that's it for my presentation.